I think the first word is always the hardest part. Oh, thank you. Well, you'll be on stage as well, so it's fair. Let's go. Oh. Let's see. I don't know. Woohoo! Okay, we're on air. We're live. Awesome. It's great to have you here. I mean, wow. If I remember, so I was lucky. So I'm Stefan, but I was lucky to be able to start or help starting the first SQA conference 2022 in Finland, and wow, has it grown since then. I mean, look at this room, quite many people interested in that field. That's awesome. So it's really great to have you, and I think we can proudly say that we are now here, the leading conference on superconducting qubits. I guess there's hardly an event that is so specialized and so big, so thank you for that. And well, I'm not alone here. I'm joined by Lisa, who has helped a lot with organizing together with a team of Scaling. And well, it's really an honor to be here. So I guess there are now people in the audience that have seen more SQAs than I have. I was not on the last one, but it's really a pleasure to have all of you. And
maybe I have to also say, welcome to our hometown. Welcome to Gothenburg. It's, yeah. And to give like a quick intro to that, I usually describe Gothenburg with 3 things, which is nice people, bad dad jokes, and very rainy weather. Luckily, we managed to completely wipe out the 3rd option, but I really hope you get to enjoy the first 2.
Yeah, I was lucky enough to enjoy a lot of dad jokes already, so I can promise Lisa's pretty good at that. So, what's up today? Today well, you see us, okay, that's the boring part. Then we have welcoming words from the Quantum Sweden Innovation Platform from Zaid. We have the the welcome by Giovanna, who has led the scientific committee, which is awesome, which has assembled this awesome program. Then we have the keynote. We're all excited for that. And we've received the abstract well in advance, so you've probably all read it. And after that, we continue with the welcome reception. And we do have a bunch of thank yous to say. Thank you for all people who served on the committee, who made actually the selections of the talk.
And thank you, of course, to all the local staff and the volunteers that will help us keep the days running smoothly.
And a big thank, well, you can clap. I think that's fair. That's fair. And a big thank you to all the companies and partners who supported SQA conference, because without you, it would not be possible to have such a big, such a cool event. And yeah, I think we got the question if there is food today. I'm really wondering if there is another SQA conference around that doesn't serve food, because we've always done this, and I think we'll continue to do so. And it's only possible because we have such great support. So you can see them all here on the logo, on the supporter wall back there. Quantum Machines, Q-Blocks, Qnity, Zurich Instruments, Roden Schwartz, Leiden Cryogenics, Orange Quantum Systems, Telin Microwave, Alice and Bob, well, now it's getting small, IBM Quantum, Intermod, Arctic Instruments, Delft Circuits, Keycom, Y Quantum, QMIL, Keysight, Cruise, Maybell, Bluefors, Quantrolox, Qtra, Silent Wave, Peak Quantum, H-Qubit, QFox, Vasta, Planckian, oh, I need water, Q-Design, Quantware, Radial, Sweden Quantum, Nord Cryo, Rigetti, Semicon, and Physics World. So I think that deserves a huge applause.
Yes, a big thank you for everyone that is here, present with us, but also everyone who's watching the stream, which is available free throughout the week, actually.
Awesome. And, well, you've seen us, Lisa and me. And if you have any questions throughout the week, feel free to reach out to us. We try to be around everywhere and help you with any requests you might have. And we are not alone to welcome you. We would like to ask Said now to also, on behalf of the, well, do I get it? Quantum Sweden Innovation Platform, to have some words to you.
Thank you, thank you. it seems to me that these two amazing people have managed to thank everybody but themselves and the planning committee. So please help me in giving a round of applause to Lisa and Stefan for bringing us all together here today. I am but one of the many representatives of QSIP who are today supporting this amazing reception and kickoff of what's going to be a great week ahead of us. QSIP stands for Quantum Sweden Innovation Platform. It's an ecosystem, a community of actors ranging from industrial corporations to academic institutes to startups like Scaling and many other companies around in Sweden that have converged together to facilitate innovation around quantum technologies in general. We are not only in Gothenburg, we are across the whole of Sweden, and the intention is really simple. Our vision is to put Sweden on the map and contribute to the global community in bringing commercial research and also innovation to quantum technologies. Not going to stretch this out. I would like to, again, welcome you all so much on behalf of the whole Swedish ecosystem and the Swedish community to a very unusually sunny Gothenburg. I hope you enjoy the week, and I look forward to listening to all the smart things we will be sharing together and exchanging notes this week. Thank you.
So hi everyone, I'm Giovanna Tancredi, and I'm here as the chair of the scientific committee. So I welcome you all here, and I hope you really enjoy the program that we have put together during these days. I don't know if you know, but Chalmers has a very long history in superconducting technology. They started in the 80s with Tord Claesson, and then later on with Per Dalsing, Göran Johansson, Göran Bendin, they established this strong asset in research at Chalmers and in Sweden in general. And today, thanks to the Wallenberg Center for Quantum Technology, we've been able to broaden our expertise that goes now from quantum sensing, fundamental physics device, quantum chemistry, to building large-scale devices. So we are very happy that you are all here and that we are going to tackle some of the key issues in superconducting technology during this week. And on behalf of the committee, I also wanted to say that we hope that during this week you will have some new clever research ideas. You will also foster new collaboration and enjoy this really nice event that we have put together. And then it's my pleasure to introduce the first keynote of this conference. He doesn't need an introduction, as I see him as one of the fathers of circuit quantum electrodynamics, for which we are all grateful in this room, with his seminal work in 2004. So please, Andreas, welcome to the stage. So Andreas Woraf from ETH Zurich that is going to talk to us about quantum error correction with superconducting circuit. Thanks.
Thank you very much. All right, so I'm honored to be here for the SQA conference as the first speaker. It's great to see so many of you here. Maybe before I get going, I'd like to say that my mother passed away just earlier this month. And I would like to dedicate this talk to her. And it's my first talk that I'm giving after this happened. All right, so you don't have to be too sad for me. I just also thought that she got 85, so that's a quite blessed age, but it's always a bit rough on this transition also for my family. And so if you ask me how I'm doing or so, yeah, then I take it with a grain of salt. But anyhow, so good. So I'll be talking about quantum error correction with superconducting circuits. The work has been done at ETH Zurich with a team that is listed here. I've thought a little bit about what to talk about during this presentation, and we decided to present some work that we're still in progress doing related to doing lattice surgery experiments on larger superconducting devices. And you see the chip that we're currently working on here on this title slide, and I'll explain it a bit more in detail. And so at ETH Zurich, we've been working on superconducting circuits for quantum information processing since 20 years, or a bit more than 20 years now. And beyond everyone who's listed on this title slide that is part of our current team, we've also benefited from lots of very good work from former members of our lab, and I think I've seen already quite a few of you here, so maybe we can get together during this meeting as well. So this work is also, in particular, the quantum error correction work is done in collaboration with the team of Markus Müller at RWTH Aachen and the Forschungszentrum Jülich, and also with Alexandre Blais' group at the University of Sherbrooke. All right, so that's our current team, or a photo of a good fraction of it. It's quite a few. This photo has also all the kind of the undergraduate students and the summer students that work with us. And if you want to work on things like error correction on large-scale devices, you sort of need a sizable team to address all the different challenges there are. And as I said already, I'm very grateful to also the past members of our group and our collaborators. All right, maybe just for a little bit for the introduction, or so you all know about this. So in quantum information processing, you're trying to solve problems that are unsolvable on conventional computers. And okay, so what are some of the examples that you all know about? The examples are, for example, solving interesting quantum chemistry problems, maybe modeling solid-state physics, for example, or maybe trying to break RSA or other codes. And for even the most basic algorithms that actually provide an advantage beyond conventional computing, you need hundreds of flawless qubits for quantum chemistry experiments, or for quantum chemistry problems. You would need maybe a couple of hundred flawless qubits that you can run deep algorithms on. And so since our qubits are not perfect, and they will probably never be truly perfect, we'll have to think about what to do. And in particular, the current error rates per operation in superconducting circuits are somewhere in the range of 10 to the minus 3 to 10 to the minus 4. And there's probably room to improve that further. But likely, these operations won't get infinitely good, because you essentially operate these systems in an analog fashion. So here in the background of my slide, every one of these red dots kind of symbolizes a qubit that you could do a quantum information processing task on. So the way forward to deal with these error-prone physical qubits is to do quantum error correction. And in quantum error correction, you need to add to the qubits that you do the computation on an additional set of qubits that you use to detect errors. And these are typically called auxiliary qubits. So the data qubits in the slides that you will see today are always shown in red, and the auxiliary qubits come in two flavors, green and blue ones, that detect either bit flip or phase flip errors. So when you want to use, or when you want to create essentially perfect logical qubit at current error rates, or logical qubit good enough for executing these deep algorithms that are needed for these use cases that I've mentioned to you, the current overhead per logical qubit is about a factor of 1,000. So when you need 200 essentially flawless qubits, with this overhead factor, you will need about 200,000 physical qubits. And in the end, we would probably not only want to solve the first algorithm that would be challenging conventional computing approaches, but we would want to go beyond that and solve more interesting problems, larger scale problems. And so this means that we have to build these large systems. So in solid state architectures, our qubits sort of live in the plane on a surface of a device, or it's maybe thinkable that qubits could live in different layers of this device, but we're maybe missing some of the flexibility that these mobile qubits like ions or Rydberg atoms have. So in solid state architectures, we typically plan to lay out the qubits in a plane like you see here. And then these qubits typically have couplers or couplings to their neighbors. And while it's thinkable to realize longer range couplers, and there's some work on that, sort of a basic standard architecture that drives many of these developments are these square lattices like the ones that you see here. And so in these square lattices, you then essentially use the auxiliary qubits that sit in the center of each one of these plaquettes to detect bit flip errors and phase flip errors. And here in our lab, so we have been thinking and working on experimental realizations of quantum error correction since quite a while, and our efforts have made, I think, some worthwhile contributions. So, for example, a few years back, we have been able to realize for the first time repeated quantum error correction in a distance 3 surface code. And if maybe Stefan remembers that, I think I may have talked about that on the last SQA conference that I was standing on the stage, which was the one in Helsinki. Okay, so we're working on error correction in superconducting circuits, trying to make logical qubits in the surface code. And we also have an effort on doing logical gates between logical qubits. And one of the approaches that you take to achieve that is to perform so-called lattice surgery. And it's a technique to perform gates between logical qubits when your qubits are laid out in a plane. And so we've been working on that also since quite some time. And about a year ago, or maybe a year and a half ago now, we actually had some results in which we demonstrated some basic step towards doing lattice surgery on a 17-qubit device, and these are published in this article that is listed here. And today I want to talk about a larger device, this 41-qubit device, in which we are trying to improve on this lattice surgery effort and make it do steps towards eventually doing logical gates between logical qubits. So one thing that I want to still comment on, so I mentioned that you would likely need hundreds of thousands of physical qubits, or maybe even millions of physical qubits, and you need to think about architectures for doing that. And likely, and this is also something that our lab is working on, but I'll not be talking about today, is you will likely need some level of modularity in your quantum computers. So I don't think it's super likely that you will have millions or tens of millions of superconducting qubits on the same device. And even if you were thinking about a monolithic architecture, it would probably be good to have some level of modularity to assert good yield for the qubits that are on your device or on your module. And then in the end, you probably want modularity to assemble different chips to each other, with each other into a larger system to, in the end, get towards the qubit counts that you need for large algorithms. And so creating modular systems that connect different chips to each other, or maybe even chips in different packages, or potentially chips in different cryostats, to each other, to me, seems essential to build large-scale systems. And this modularity is then probably also useful for practical reasons, to first allow for scaling to larger systems, but also to be able to maybe swap out part of your system for some more modern version of a device or some more modern infrastructure without disrupting your whole large-scale system. And in the end, there's probably some level of serviceability needed. And if you think about how HPC computing centers or how HPC computing systems look like, they're not just one monolithic large-scale computer, but it's usually a networked system of many kind of powerful individual computers that are hooked together with networks. So I do think this is something that will be necessary, actually not only for superconducting circuits, but essentially for any modality with which you would try to realize quantum computers. All right, so in quantum error correction, there's additional challenges. Error correction, conventional error, like classical error correction or regular error correction is used a lot also in conventional computing. So the memories in your laptops and in your phones are error corrected. And for classical information, it's good enough to deal with bit flip errors, zeros turning into ones and ones turning into zeros. But in quantum computers, you also deal with superposition states, so you have to correct phase flip errors as well. And maybe the main challenge there is that in contrast to classical information, you can't just check the information stored in your register, because if your register is in a superposition state, that measurement would collapse that superposition state into one of the eigenstates of the measurement basis. So you have to think of more clever ways how to detect whether errors occur or not, and then quantum error correction. One of the approaches to do that is to store the logical information of your logical qubit in a system of physical qubits, like the one that you see here on the right, which is a square grid of 5 by 5 data qubits shown in red. And you try to store the logical information in a logical in the state of the set of 25 physical qubits in a way that there are certain symmetries of that state which are preserved. And the symmetries that are commonly used is the parity of that state. So you could decide, for example, to store all the logical information in quantum states that all have the same parity. Say they're all even states. And then your error correction approach would work in the following way, that you would check whether the states still are of even parity. And any time that you see the parity of that state change, you learn nothing about the state itself, but you notice that an error has occurred. This essentially enables you to perform measurements on your logical state while not learning anything about or perform error detection on your logical state while not learning anything about the nature of the logical state. Okay, so in our lab, we still focus on the surface code. Until maybe a few years ago, the surface code was essentially the best well-known or the best code, which had the best properties for realizing error correction. It had a large threshold error and provided a reasonable scaling with a physical error for any of the operations on your qubits. So in the surface code, the logical error of the logical qubit scales with the ratio of the physical error per physical qubit divided by this threshold error. And as soon as the physical error is smaller than this threshold error, and you can make large enough lattices of qubits, you can essentially exponentially suppress the logical error in your logical qubit by just assembling more physical qubits with each other. And so this quantity d here is the distance of the surface code, and it's essentially the number of qubits along one of the dimensions of this 5 by 5 surface code lattice that you see here on the right-hand side. And in principle, for example, if in your lab you verify that you can make an arbitrary number of physical qubits at constant quality, maybe by using modularity, for example, you would in principle say that you're always able to make the logical error as small as you want by just using more physical qubits, making the distance of the code larger. Okay, and then the surface code is also useful because it's amenable to these 2D architectures that are easier to realize in solid-state systems. Good, so how do you measure these symmetry properties, the parity of the logical state stored in the data qubits? So the data qubits, as I said, are the red ones. Yeah, the auxiliary qubits are the blue and the green ones. And the auxiliary qubits sit in the center of a plaquette formed by the data qubits that you see here. And you use this auxiliary qubit in the center to measure the parity of the data qubits on the vertices of this plaquette. And this parity measurement, it's also called a stabilizer measurement, and formally it corresponds to measuring the product of the Pauli Z operators of the data qubits that are sitting on the vertices of this plaquette. And so now, like in a simple way or a convenient way to measure this parity is, like this operator here, is to use this auxiliary qubit and to essentially run C0 gates between every one of these data qubits that sit on the vertices of this plaquette here and this auxiliary qubit. And so now you could easily see if an even number of data qubits are in their one state, the auxiliary qubit value or the auxiliary qubit state will be flipped an even number of times. And if you flip that state an even number of times, it will be the same after this set of gates as it was before this set of gates. So when essentially the parity is even, the auxiliary qubit state effectively doesn't change. And you can check that by reading out the auxiliary qubit at the end of this gate sequence. However, when, say, one of the data qubits flips from 1 to 0 or 0 to 1, the parity will then change from even to odd. And now you have an odd number of C0s between your data qubits and the auxiliary qubits. And if you have an odd number of C0s, the auxiliary qubit state will then swap. And this you can detect using the measurement of the auxiliary qubit. Okay, so this works for these bit flips. And you would do that in one round of error correction. You would do that for every one of the plaquettes that you see in this distance 5 surface code. But since we have to take care of not only bit flip errors, but also phase flip errors, there's these other plaquettes which are interleaved, which have blue auxiliary qubits in the center. And with these other plaquettes, we actually measure the parity in the X basis. And the parity in the X basis corresponds then to measure this product of X operators, again, on the vertices of on the data qubits which sit on the vertices of this plaquette. And you can turn this gate sequence in measuring parity in Z into measuring parity in X, essentially by flipping or by rotating the basis of every data qubit before this gate sequence, running your gate sequence, and then rotating your data qubits back. And in a single round of error correction on a logical qubit, you essentially run these gate sets for all the plaquettes that you see on this slide. And for this to work, it seems quite apparent, that all these elements need to work well enough, so that you actually faithfully extract the parity information from this set of data qubits. Good. So that's sort of what I want to say about sort of how this error correction works. And then when you run an error-corrected algorithm, like on every logical qubit, you will continuously run these parity checks to try to notice whether errors have occurred. And from the information that you can extract about the errors that have occurred, you can actually devise a strategy that allows you to correct for these errors. Okay, and then the next question, that, like once you have these kind of memory qubits available, you could then ask yourself, okay, how do you run gates between these memory qubits? And the work that we're currently mostly focused on is to try to entangle logical qubits with each other as a first step towards realizing gates between logical qubits. And for that purpose, we made a device that has this set of qubits here. So these are, if you were to count them, these are 41 qubits. They sit in this square lattice. Yeah, you see the red and the blue and green qubits are the data and the auxiliary qubits. And every gray bar corresponds to a physical coupler between qubits that are connected by that coupler. So the device that we've made for working with this geometry looks slightly different from that, or it's slightly distorted. And the way how it's distorted, I try to show you in this animation. So it's kind of this lattice is squished, and when you will now look at the device, you will see this squished lattice. So we squish this lattice in the following form by kind of pressing the qubits to each other. And now the topology or all the connectivity is exactly the same, but the arrangement of the qubits in space somehow looks slightly different. And this is how the qubits are laid out on our device. All right, so here's a picture of that device, or a part of that device. So it has 41 qubits, and it has a few extra qubits. And usually my saying is always, it's a bad idea to have something on your device which you don't really need. Yeah? But we thought that, okay, when this was designed or so, it was thought, okay, good, let's maybe put these extra elements on it, and now we know that we should probably have rather left them away. But there's these 2 extra qubits, and so there's also some extra couplers. So in total, there are 64 qubit couplers on this device, and every qubit, every individual qubit also has its dedicated readout resonator and also its dedicated Purcell filter. Okay, so yeah, if you've seen me giving talks before, yeah, you've probably seen some similar slides before. So on this device here, every yellow area is a transmon qubit. It's a single-ended transmon qubit which is shunted through a squid to the ground. You see it has kind of this geometry that I've tried to explain to you just before. So every qubit has its dedicated charge line to drive transitions, which are shown in pink. Again, every qubit has a dedicated flux line to tune the transition frequency, and we perform gates between neighboring qubits by changing the qubit frequency. So these are the lines that we need to initiate our 2 qubit gates. There is a set of couplers that couples the neighboring qubits in this topology or in this grid structure that I've explained to you before. Then, as I mentioned, there's an individual readout resonator that is strongly coupled to the qubit, and an individual Purcell filter. And there is some level of multiplexing in the readout, and for this 43 qubits, there's 8 separate readout lines. And if you would zoom in on one of these qubits, so here's the transmon qubit with a capacitive island. 2 tunnel junctions are here. And you see the flux line, the charge line coming from the bottom, and the couplers going into the 4 directions. Good, and so this is then what the whole sample looks like, and that's the device that we've done these measurements on. So then this sample goes into a package, or we needed to upgrade our package a little bit, so it's a 128-port sample mount. This sample mount goes into a fridge package, and that goes into a fridge, and yeah, we seem to like white gear in our lab, so our electronics is nicely in the same color scheme as our cryogenics. So this is the electronics that we need for controlling all of these 43 qubits in this setup. and all of the 8 readout lines. All right, so let me say a few words about the sample. So here's some tune-up and benchmarking results. So here you see this qubit lattice. It has a left logical qubit, so it's this 3x3 patch on the left. There's a right logical qubit, a 3x3 patch here. And there's 3 extra data qubits in the center, and then there's 4 extra X-type auxiliary qubits in the center that are used in this lattice surgery approach, which I'll say more about in a little bit. So our experiments are still largely limited by the defect density in our qubits, because and these defects, like these 2-level defects, limit our gate fidelity. And so here you see a cumulative distribution of the single qubit errors here to the left, the 2-qubit gate errors in blue, and then readout that can either discriminate 2 states or 3 states. And this is data from this device that I've just shown to you. And this here is data from this device from a few years back which we realized the first distance 3 surface code. And to some degree, you could say, the data is not much better than this old data, but it's also not much worse, besides the fact that the chip is a fair bit larger. And we're working on getting the performance of this to come up some. And we'll also see how this performance will actually limit the quality of the operations that we can do on our devices. And here, as a fraction of unity, the single qubit, 2-qubit, and the readout errors are quoted on average and compared to this earlier device by Sebastian Krinner. So the most important part of our work to improve the performance is actually these 2-level defects, and we had a paper some time ago that discusses one of the approaches where we had noticed that it appears that, at least for our fabrication technology, it looks like the area density of defects is constant. And so if you make the junctions smaller, you get less defects per junction. And this we've also verified repeatedly in experiments, and we're working on new samples that would have this reduced defect density and would then therefore we would hope that they would lead to reducing the 2-qubit gate errors. Good, so then the first thing that you do with such a large device, or you see it here, there's all these plaquettes with the data qubits on the vertices and the auxiliary qubits in the center. And there's auxiliary qubits at these triangular plaquettes that are at the edge of the bulk of this lattice. And you would go ahead and measure these stabilizers by essentially preparing all the data qubits on each one of the plaquettes in all the possible basis states. And then you would just run this gate sequence that I had just explained to you. And whenever the stabilizer comes out as 1, you measure an even parity. And when it comes out as -1, you measure an odd parity. And you see that this parity measurement is essentially has an error, which is quoted here. And the error comes from the accumulation of all the gate errors and the readout errors. Okay, and so there's weight 4 stabilizers, so ones that sit on these squared plaquettes, and then weight 2 stabilizers on these triangular plaquettes where you just measure 2 data qubits. So here there's the set of all the stabilizers on this device. And so the average weight 2 stabilizers, they're better because they have fewer gates, because fewer qubits are involved, is maybe around a little bit less than 5%. The average error on the weight 4 stabilizers is around 10%. And so you can compare that to other results that we had previously. Here's again this Krinner paper from a few years back and this larger device. And you see that they're doing similarly well, and we would hope that we would be doing better, but that's the way it is on this current device. Okay. So what can you do then? So we have this large device, and so it has a patch with one logical qubit at the left, a logical qubit at the right, and a few physical qubits in between. And so you can first run these logical qubits individually. So here's a picture of what that looks like. Here's the logical qubit on the left. It defines the logical Z and the logical logical X operators for the qubit L1 on the left. And on that, you can run a gate sequence that would essentially correspond to a memory experiment with a distance 3 surface code logical qubit. And there are sort of some dynamical decoupling pulses played in our gate sequence. So here's the same thing for the logical qubit on the right. And the gate sequences are slightly different, and the reason for that is that we had to adjust the gate sequence slightly to deal with the defect configuration that we found in that particular instance of a cooldown of this device. So when you run these logical qubits, you can repeat the experiment that we've done some time ago and prepare the logical qubits, initialize them in their ground state, in their excited state, or any superposition state, and then run your error correction cycle a number of times, and the cycle number is written down here. And then from evaluating the logical the expectation value of the logical Z or X operator and plotting it versus this the cycle number, you find this decay in the logical expectation values. And the decay will give you the logical error per cycle, which for the left logical qubit is not particularly low. It's about 7% or so, and it's mostly limited by some unfortunate combination of these two-level defects. So the one on the right is doing slightly better, even though that the hardware is very similar. It's really the only really main difference is the instantaneous defect configuration on this right logical qubit. So there the error is about a little less than 4%. So this is when you run these two logical qubits independently, and one of the things that you would want to test is then whether you can run the two logical qubits simultaneously and whether they perform equally well. And so here's a picture of that. So here's the gate sequence when you run them simultaneously. So here's all the 41 qubits, and you run this gate sequence, and you see how that performs. And it performs equally well or equally bad, you could say, depending on what your perspective on this is. But what it shows is essentially that there's no level of crosstalk that would deteriorate the individual logical qubit performance just by the matter that you would operate them both simultaneously. So that's probably something that you would want to verify on your device. So this was now essentially distance D surface code experiments. And I've mentioned to you, like our lab had done sort of the very first repeated surface code experiment in any superconducting circuit architecture. There were these ion experiments slightly earlier, and so here's kind of a complicated plot that I've maybe not enough time to discuss, or so. This shows the logical error per cycle. So this was our first experiment. Our current experiments are still kind of here, and now if you look, there are some experiments that have lower error per cycle. And maybe the thing to call out is this Google experiment that has done distance 3, 5, and 7 and extracted the error per cycle and has demonstrated this exponential scaling of, or exponential reduction of the error with increasing distance. And there's also some data sets that come from ions or Rydberg atoms. And one of the things that you see here is that if you extract the cycle time in these different systems, the typical cycle time is about a microsecond, or the cycle rate is about a megahertz for superconducting circuits, while it's typically a lot slower for atomic systems. And so this is maybe one of the metrics where superconducting circuits could do well relative to atomic systems. Okay, so let's move on towards lattice surgery. So okay, there are surface codes. Distance scaling has been shown in these memory experiments. And okay, now you would want to move ahead and move towards doing gates between logical qubits. And the approach that one would use is this so-called lattice surgery approach, which you see here sort of schematically, where you have this distance 3 patches and some qubits at the interfaces. And you do specific operations to have these different logical qubits interact with each other and effectively perform gate operations. Good, so there has been prior work on logical qubit operations, which I try to summarize here. So there's been some logical operations on encoded qubits with superconducting circuits and ions. There have been some non-fault tolerant arbitrary state preparation in different systems, and there's been a set of working on independent logical qubits. And the thing that we are after now is to perform these lattice surgery experiments. There have been some in ions, some on these distance 3 CX and Bacon-Shor codes. And there's been also one by one of our former grad students who did this experiment here during an internship at Google. And then there's efforts trying to do lattice surgery with superconducting qubits, and there's our work on splitting a distance 3 surface code into 2 distance 3 repetition codes. And then earlier this year there were these 2 nice papers by 2 groups from China that are listed here. Okay, so when you want to perform gates between logical qubits, for example, if you're in an atomic system, one very nice thing is if you would perform C0 gates between physical qubits, and you are able to have pairwise interactions between physical qubits, you can do a so-called transversal C0 gate, where having C0 gates acting between pairs of physical qubits from different logical qubits translate to having a C0 gate acting on the 2 logical qubits. And so this requires the right connectivity, which you can realize in Rydberg atoms, for example. So when you have a 2D square lattice connectivity, kind of this is not realizable, and you have to think about something else. And in fact, like when surface codes were thought of, like this lattice surgery approach was developed fairly early on. And so in these lattice surgery approaches, you have these 2 patches of distance 3 surface codes that you see here. And you could either merge these 2 distance 3 surface codes by using 3 data qubits in the center and 4 X-type auxiliary qubits at this interface, merge it into a large patch, as is shown here. And then you can split it again in 2 individual patches by essentially measuring out both the stabilizers and the data qubits in the center of this patch. And if you do this in the right way, you can entangle logical qubits with each other. Okay, and so we had worked on that on one of our smaller devices, on a distance 3 surface code that you see here, which is just this 3x3 patch. And you can sort of do the essential parts of this process by considering these center data qubits as being the qubits at the interface between 2 distance 3 repetition codes at the edges here. So what you would do, so here's the distance 3 surface code qubit with its logical operator definitions, the logical X, the logical Z operator. And to perform a lattice split operation, you would essentially stop measuring these 4 X-type auxiliary qubits, which measure the parity in the X basis. And you also read out the data qubits at the interface between the 2 logical qubits. And what you end up with when you do that is 2 distance 3 repetition code qubits, one on the left and one on the right. And there then is, through these measurements, you establish a relation between the logical operators of the distance 3 surface code qubit and the 2 repetition code qubits. And so in this earlier experiment that is published already, and that came out only in the beginning of this year in Nature Physics, we had essentially shown that using this lattice surgery between turning 1 distance 3 surface code qubit into 2 distance 3 repetition code qubits, we could entangle the 2 repetition code qubits with each other. But since the repetition code only corrects for one type of error, it was only protected against bit flip type errors. And so that led to the situation where the ZZ expectation values between the logical qubits were high, but the expectation values of the XX and the YY were much lower. And then so in that experiment, we also did perform some of the steps that are needed to characterize these logical quantum states more, for example, to be able to do a logical process tomography. And so on this larger device, we can now see how this works with more qubits, and where we can now not only be protected against bit flip errors, but also against phase flip errors simultaneously. So here's this device. So I've explained all the basics to you already. This is this 3x7 patch, so with its 41 qubits in total. The two logical operators are indicated here, Z and X. And we split this large patch into two logical distance 3 qubits along this path here. And we do it in the same way that I've explained already. You essentially stop measuring these 4 X stabilizers, X5, X6, X7, and X8. And we also read out the data qubits at the interface. And so in this way, we've split this 7x3 surface code patch into two distance 3 surface codes. And the concept works essentially the same way. So what you need to do to entangle these two distance 3 logical qubits with each other, you need to perform this Pauli frame update. You need to make use of the results of the readout of the data qubits and these auxiliary qubits to essentially correctly update the logical states of the then two separated distance 3 logical qubits. And the update rules are the following ones. Yeah, so the X1 logical operator and the X2 logical operator, you can extract from the logical X operator of the 3x7 surface code patch by multiplying it with these stabilizer values. And these 4 stabilizers here are the 4 that you extract from reading out the stabilizers of these 4 blue auxiliary qubits. And similarly, for the logical Z operator for the individual qubits, there's this relation that holds that you can evaluate by making use of the measurements of these data qubits here. And then in the end, for turning this sequence and verifying that the two logical qubits are essentially entangled, you need to use these measurement results and sort of do the right basis rotations on the two logical qubits. Okay, and this is what we've done or so, and this is now fault tolerant in bit flip and phase flip. After you've and it creates a logical Bell state after you've performed this Pauli frame update, which I've explained to you. And so ideally, like for any Bell state also in a physical basis, there's correlators between the X observables in the two entangled qubits, the Z observables and the Y observables that are ideally plus and minus 1. And so these you can evaluate from running the surface code split operation on these devices in the following way, yeah, and evaluate these logical expectation values. And the dashed curves are what you would be expecting, yeah, and the colored bars will be experimental result. So one of the things that you can do is now that you detect errors all the time by analyzing parity measurements with your auxiliary qubits, you can post-select on instances where there were no errors at all, yeah, because if you have pretty good parity measurements, yeah, you can tell from those whether an error has occurred, yeah, and without trying to correct for these errors, you could just see whether your approach works when you just run your system in error detection mode. And so this is what is shown here. So if you just detect errors or so, you get the expectations for the ZZ correlator, for the XX correlator, and for the YY correlator, essentially in the way you would be expecting. And so now, in comparison to the easier split experiment on the two repetition codes, because it's now error protected also for bit flip errors, you see that the XX value now is also large. And the YY values are always limited by the fact that the way they get extracted is it is not fault tolerant, and therefore you can't reconstruct the full Y value. All right, so this is just post-selected. This is not really what you want to do. And you could also just run your surface code and pretend you are doing nothing and just read out the logical operators at the end. And then you will essentially see that all your expectation values are essentially all 0. Okay, and now you would run your surface code decoder for this process, yeah, and you would hope that when you run this decoder that you get close to kind of the post-selected expectation values. And there is now something where we would say, we would hope that this was much better, and we just see it barely starting to work. And we're still in the process of trying to find out what exactly limits this this performance. So the decoded values are, so you see that they recover from the raw values some of the expectation values, but we're far away from finding unit expectation values. So I think this seems to show that this decoder and the error correction sort of starts to work, but there needs to be some improvements in the ingredients of running these gate sequences and moving the device beyond the threshold. So maybe one of the things that I have not mentioned, this early device, the Skrinner paper from 2022, was near threshold, within a factor of 2 threshold. Yeah, this device is not better, but does many more gates and more complicated operations. Yeah, and this you see and you pay for, because the deeper your circuit gets, essentially the performance gets worse rather than getting better. But what is nice for us, we see that this works, and so we are now, in principle, we're ready to sort of swap out for a better sample, do exactly the same, and then see how this gets better, which is our approach. All right, so to summarize, we've demonstrated lattice surgery both in this small version, where we split the distance 3 surface code into distance 3 repetition codes, and then we have started to work on this split experiment on this larger device, and it starts to work, and I'm pretty hopeful that we'll be able to do this better in the future. And so the next steps here, and we actually do have some data on that. We've also performed merge operations on this device, and also logical state teleportation, but since this data is relatively fresh, I think there was not enough time to really prepare it at a level that I could present it here today, and there's also not enough time in my talk to still look at this data either. All right, so what to do better in the future? So we would like to improve the performance by getting qubits with lower defect density, and I've mentioned to you already that one of our approaches is to get better junctions, which are smaller and have then less defects per junction, which are still the main culprit in limiting our 2-qubit performance. And we do have first devices which show that that's actually the case, but we have not been at the stage yet to fully deploy it for these kind of more complicated experiments. And then the other thing that we're also hoping for is, I've talked a little bit about modularity and how this is important generally. So we have a work stream that looks at modular devices, and we would also hope that going for this modular devices, we can be sort of better at selecting modules that have good performance and then putting well-performing modules together on these bigger devices. And here you see an example of that. And I would also hope that that in the coming months or next half year to a year, we'll be able to show some more results on these modular devices. And there are a couple of papers out already on smaller versions of these. All right, so I'd like to thank our current team again. I should maybe call out specifically Luca Hofele and Yongsin Song, who are 2 of the graduate students who really worked very hard on this, in particular in the last couple of months and also in the last couple of weeks to put these plots together for the slides. But there's a larger team at ETH that works on this to make this all happen. And if you're trying to run experiments with tens of qubits in your lab, you probably know that this is hard. And credit goes to our team here. And yes, as usual, we're always looking for good people to join our team and bring these experiments forward. So thank you very much.
Thank you very much for this very nice, informative talk. So now it's time for some questions. Don't be shy. Yes, we have one there.
Thank you for the very interesting talk. I have maybe a very basic question regarding the errors, because so as I understand, by introducing additional qubits, you are reducing an error, but these additional qubits, they can also produce the error itself. So how do you deal with them?
Yeah, so the magic of error correcting codes takes care of that. So it's protected. It can identify both errors that happen on the data qubits and errors that happen on the auxiliary qubits as well. And I've not said anything how you actually do that. So what you essentially in the end do, you have this big patch with data qubits and lots of auxiliary qubits. And in one cycle, you read out all of the auxiliary qubits. And then you do another cycle and you read out all of the auxiliary qubits. And what you get is a pattern in space and a pattern in time where you see your auxiliary qubits either not change state or change state. And this information, like the way how the auxiliary qubits change state, you can use to identify what errors actually occurred. And this includes errors on the data qubits, but also errors on the auxiliary qubits, because the temporal sequence of the errors that you observe depends on exactly what type of error was detected. And this you can work out, and in the surface code, and in all the other codes, it's such that you detect and can correct for errors on both data and auxiliary qubits.
Thank you.
There's one up here, and then Tim.
Hi, thank you for the nice talk. Is there a particular reason why you stick with the 4x stabilizer versus, say, an XZZX or a ZXXZ type stabilizer circuit to try to balance between bit and phase flip errors?
Probably not. I think so for example, when you ask, I think the challenges in these experiments, at least, I mean, we're an experimental lab. Yeah, there's many challenges on the experimental side. Yeah, and if you're like, once you've overcome your experimental challenges, you can kind of relatively easily try these different codes, yeah, and change for ones that combine Z and X stabilizer measurements. And this we would be interested in. And I think one of the stages that we want to reach with such an experiment, for example, it's a sizable amount of work to make it work at all. Yeah, and once it works, yeah, you can or works well enough, then you can sort of try out things on this device. And I hope that we will get closer to sort of trying out things and wondering, for example, whether better codes could be more suited to the types of errors that we see. And so when you ask, so what is the dominant error source in our devices? Yeah, the most annoying thing is still these two-level defects. Yeah, and I mean, there's ways to mitigate them, and we've tried out some ways to mitigate them, both on the fabrication side and on the device side. but some of them for example, you could try to tune the defects away with DC gates, and we've also worked on that. But to integrate this in a large device is kind of challenging. Yeah? So we're totally happy to try out different codes on these devices. And I mean, there's, for example, Nathan Lacroix at Google has done this color code experiment on a thing that was made for the Surface code, and it was very interesting and worked quite well as well. There were some questions there. There's Tim, and then this gentleman there.
Hi, thanks for the talk. I wanted to ask, in the fabrication process, as you mentioned, what is the reason, or what's the main source of the TLS density?
Yeah, if we knew. So, yeah, I think this, for example, every now and then or so there's a, so what would you wish for if there was one, if you had one wish free, and if you ask it to a superconducting circuits experimentalist, you would probably, one of the good answers would be, okay, get rid of strongly coupled TLSs and everyone's lives would be much, much better. And I think the performance of all of these things would be way better. And if you look at, if you dig enough into kind of the supplementary material of all these papers, yeah, you'll find that it's mostly TLS limited. And I think better research on materials and fabrication processes would hopefully get rid of that. And yeah, Rydberg atoms and ions don't have TLSs, so that's maybe one of the things that makes things easier on that round for them. And to do careful device development, fabrication process development is something that is very meaningful, but also very hard, and even in kind of dedicated clean rooms of companies, this is hard, and we're still in a university clean room, or in 3 different university clean rooms, and it's yeah, I think it's a challenge to make it work at all, even at this level.
Thanks.
So if you get rid of TLSs or so, everybody will be super thankful, and you should maybe try to patent it or so, or maybe you should not patent it at all, so that everyone can benefit from it.
Thanks, Andreas. I had another question about the TLS. For those of us not experts in error correction, I wonder if you could give a bit more insight to what channel does this, how does this really, you know, does it because it affects the distribution of T1s? Is it the readout channel? But how does it really?
It's even more basic than that. So one of the, okay, good. So maybe the other thing that is special about these devices, and you could say, okay, this is maybe a poor choice, but one which we made. So if you look at all the other experiments that are around there that maybe perform better than ours, they have tunable couplers. Yeah? Our experiment doesn't have tunable couplers, it has static couplers. And the qubit gates are initiated essentially by having qubits that are at an upper sweet spot at a high frequency and a lower sweet spot at a low frequency, and the 2 qubits interact with each other by tuning them into resonance with each other. And these defects are essentially distributed in frequency space, and like how well your gate will do depends now on where are the defects, where are they in frequency for the qubits that are involved in the gate. So, and the worst thing is if you have a defect that is resonant with the qubit at its idling frequency or so, that this will essentially kill the qubit, or you have to then move it off this off the sweet spot, which will make it really bad. And you have to kind of choose interaction frequencies, and this is annoying. And then the second thing that is annoying is that these defects vary in time. Or it's like even if they sit there nominally, they drift, and it's maybe also not that surprising that they drift because you run pretty strong pulses on your chip all the time, and this essentially kills our gate calibration. And I mean, Google had this paper or so where you can maybe try to use surface code data to kind of tweak your gate calibration as you go, and using some machine learning approach. Yeah, so. But it's really, I would say, it's the effect that the mere existence of the TLSs has on the ability to do good 2-qubit gate tune-up. It's not that there's sort of a very specific error channel that comes from that, because if you, at least at our level, if you then look at it at the end or so, I think at least in our, we've not yet looked at it for this paper, but in the Krinner paper, if you look at error correlations, it all looks pretty normal. It looks like errors are uncorrelated, and multiple errors occur with probabilities that are just the product of individual errors on this level of error scale.
One last quick question.
There's someone there. Oh, there's two different ones there. Oh, okay, good.
Hi, thanks for the nice talk. I just wanted to ask, what kind of decoder are you using for error correction, and how are you dealing with leakage into higher states?
Okay, good. So this is with a minimum weight perfect matching decoder or so is what we do in our memory experiments typically, and they are trained using measurement data. So we measure correlators, and we don't use a physical model, or we don't use a theoretical model to set up the weights for our decoder, but we use measured correlations to set up the weights for our decoder. And there's a paper by Ans Rem or so which discusses that in some detail. And we were facing some issues with that on these more complicated experiments, which we're still trying to figure out. Yeah? And currently, for example, if you want to get better, lower logical errors, you want your hardware to be better. There's maybe a little bit of room by doing better decoding. But you could do much better by just having your hardware be better. And the second part of your question was what? Leakage. Okay, good. Yeah, so I've also not mentioned it. So this is also still post-selected on no leakage. All of these experiments, the Krinner ones were as well. There's a number of papers for leakage reduction units. We also have our own leakage reduction unit. We've deployed leakage reduction units in our experiments. One of the problems is that these leakage our dominant leakage source is 2-qubit gates, or MISC, not perfectly calibrated 2-qubit gates, because in the gate scheme that we use, we cycle through the second excited state. And our leakage reduction unit, you would not like to run it after every gate, but maybe once per cycle in a stabilizer or so. And then you have to think about how errors propagate, say, depending on where the error within the stabilizer execution occurred. And when the error occurred early, it can mess up later gates. And you need to have sort of a leakage resilient gate, which we also have. I mean, I've talked about that, but we still don't have the paper out. So there's things that one can put on top of this, but the data that I showed was all leakage post-selected, and you could say, okay, good, that's slightly cheated, and you would want to do it differently, but currently we were not at the stage yet to really put this together. And these leakage reduction units, like in these bigger experiments by Google, if you have larger distance codes or so, then larger distance codes can deal with some level of correlated larger weight errors, and these correlated larger weight errors tend to occur in these leakage settings, and you need to sort of systematically deal with it, and it's a bit challenging. I think we have the bits and pieces together, but we're not there to deploy it. I mean, we've tried to deploy it, but with no really good visible improvement, and so it's not used here.
Thank you so much, Andreas. Let's
thank you.
Andreas.
Yeah, thank you so much. We have now officially gotten started, right? And that was just a glimpse of what's to come. We have so many more amazing talks, posters, etc. Maybe we should mention a little bit of what is to come. So anyone out there attending SQA for the first time, congratulations. That was a good choice. I honestly think that this is the best event throughout the whole year. It's a focus conference, single track. You can really immerse yourself. And the fact that every single person in here that you will talk to has something that's interesting, but also relevant to the work that you're doing. So really take advantage of that opportunity.
And it's also the biggest SQA so far, which I think is exciting. And I discussed beforehand that, well, I didn't lose a bet, but I really want to show this. I think that's how you do it today. You show it to the internet. I wanted to wait until the first row fills up, but I studied to become a teacher once, and it's the same in every classroom. Like, the first row never really fills up. In case you force people, that's the only way to do it. But that's all right. So I guess what we do now to encourage you to post and speak about the conference is we do this awkward selfie with all of you in the background. Sorry for that. And then, finally, we can continue with the program. Fair enough. Fair enough. That works. That was all. Not everyone is there, but it shows we are plenty.
Yeah.
Awesome.
Now we at least have proof that it is the biggest edition of SQA, and I am a little bit biased, but I also think it will be the best edition of SQA. But let's see. Time will tell.
That's a tough challenge to take. As you might have known, I'm with IQM, and we were able to start this conference with the support of the community, and that's why we never organized it alone. We've organized it this year with Scaling, with Chalmers. Otherwise, it would just not be possible. But that's not the only initiative IQM is taking on, like facilitating research and supporting researchers. And there is one other thing that Rubika, my colleague of mine, wants to speak about and share with you all, and that's why I would like to Rubika to come on stage and speak about what this is.
Okay, good evening, everyone. Thanks, Stefan, for the introduction. And yes, so IQM Research Award 2026 is basically another way, in addition to SQA conference, to give back to the research community. And this year, we launched this initiative in May. However, I started thinking about this last year in September, so it took a while, but I apologize for that. And basically what we want to do is not only offer the prize money that you can see here, but also 12 months of IQM Resonance access to the winning team. And also for those who come in second and third, we offer 6 months of IQM Resonance credits. So we ran this competition for about 3 months, and today I'm very, very happy to announce the winners. Okay, so please give a round of applause to the winning team. Virginia Tech Quantum, so VT Quantum, Department of Physics, Virginia Tech and Virginia Tech Center for Quantum Information Science and Engineering. So these are all the wonderful team members who unfortunately could not be here today, but I'm hoping that next year, when we have the second edition, then somebody will be here, at least from the winning team, to get the prize handed to them. So yes, I also want to mention those who came in second and third place, because it was not an easy fight for them either. Yes, so we have team number 2, which was Adam Bednors and Thomas Rybotsky, and from University of Warsaw, and Nicholas Copernicus Astronomical Center. And in third place was Jishnu Goswami from Bielefeld University. So these were our winners, and you'll soon see all the details of all their wonderful work on LinkedIn very shortly on our website. So like I mentioned, part of the reason why I wanted to announce the winners today at this occasion of SQA conference was that, yes, there will be another IQM Research Award 2027, for which I would really appreciate if you can spread the word in the community and also participate yourselves, because I'm sure there are wonderful ideas, and we want to increase the number of applications meaningfully higher next year. So, oops, sorry. So please spread the word and look out for our post on LinkedIn and also on the IQM website for more details. So thank you. With that, I'll transfer the mic to Philip, who will share more about the celebratory aspects of this evening. Thank you.
Hello, everyone. Good evening, and welcome to SQA 2026. I am this guy. I am Philip, and I am from Scaling, and together with Irina from IQM, who couldn't attend today, unfortunately, and Stefan and Lisa, who you have seen a few times tonight. We are your organizing committee for this amazing event. Before we start, I'd like to go through what will happen this evening. So we are at the wonderful World of Volvo to show you a part of Gothenburg history when you're finally arrived. So we will have an exhibition for you on the 3rd floor. Seeing as you are so many people this day, we're going to have to divide you into 4 groups. And I think the easiest way to do that is to way you're sitting. So this part will be group 1, 2, 3, and 4. So when I'm done talking, group 1 will go directly to the exhibition. And then 10 minutes after that, group 2 will go, 10 minutes after that, group 3, and so on. But don't fear, the 3 groups that are left, the bars are open, so you can help yourself to drinks. Unfortunately, you can't bring drinks into the exhibition zone. But when the first group arrives back from the exhibition, the food will be served as well. So thank you all for coming today. We are over 500 people at SQA this year, which is record-breaking, and enjoy the evening, and thank you all for coming. Welcome to Gothenburg.